Hello dear friends, a great welcome to the series on Idea Statica Member. Myself is Jarajan P. This is tutorial number 33 and here I will demonstrate how to verify a laterally restrained beam using Idea Statica Member with respect to Eurocode EC3 provisions. Before taking you to the Idea Statica Member, I would like to introduce you the problem statement. So here is the problem statement. We have a simply supported beam that carries two concentrated loads at the known locations. As you can see that the beam has a total span of 6 meters, and by means of the constructed top deck slab, it is ensured that the beam is laterally restrained all throughout its span length, and the material chosen for the beam is S235 steel, and the section used for verification is HA240. And based on the permanent actions and the variable actions, the values of the concentrated loads at the ultimate limit strength state check will be P equals to 90 kN, whereas for the serviceability limit state check, P is calculated to be 35 kN, which is essentially only the variable actions. The permanent actions are not considered in the SLS. Now, based on the formula given in the Eurocode, the computed plastic moment capacity of the HA240 section is calculated to be 175 kN meter. So let me take you to the Idea Statica Member for the verification of the given beam. So this is our Idea Statica window looks like. So let us start from a new project. So I'll just press new. So let us just start with the project name. So here I am going to use, say, for example, the beam1, and let me just keep this project folder. Let me just keep it in my desktop. So select folder. Okay. So now regarding the design code, we are going to do the verification of the beam using the Eurocode. And steel grade that we'll use in this case will be the S235. So let me select S235. So this is my S235. Okay. And now, okay, the concrete grade is C2530. And here we are going to deal with a beam structure. So we'll choose the first level. Okay. And the span that we are going to input here is 6 meters. So we'll just keep it as 6 meters. And let us start with a section of HA240. So let me change the section HA to HA240. So sections. So we will change this to HEA section, HEA 240. So this is my HEA 240. Okay. So okay. So we can finally press the create project button. So this is how the structure or the beam to be investigator looks like. As you can see that it has got a beginning node, it has got an end node, and it has multiple numbers. For example, referring to this what we call as the structure that we have just generated, we can see that there is an analyzed member AM1, and we have the related members. We have a related member RM1, which is essentially a beam connected with a column related member RM2. And similarly, on the other end, what we see is that we have got two more related members, that is a related member RM3 beam, and there is a related member RM4 column. So now let us start modifying this as per our requirement. So here what I want is, I want, instead of getting a list member connected to a column, I want to directly connect it to a beam. So what I would do is, I would, for the timing, let us straight away go for the AM1. So we have a HA240 that is already input into the program, and the offset will change depending upon the size of the related member. So, and as you can see that the length is already 6 meters. So let us first start deleting all these default the related members. So RM1. So what I will do is that I will simply delete it. It's a beam. So I will delete it. And RM2, that's a column, that also I will delete it. And then we have the RM3, that is another beam, that also I will delete it because I don't want it right now. And RM4, the column also I will delete. So that is deleted. So as you can see that now, right now we have only one analyzed member. Now I would like to introduce two related members in such a way that they are essentially the beams. So what we can do is that in order to introduce a beam at one end, at both the ends, can let us go straight to the connections. And to the connections, what you do is that we want a continuous. So when we press CON1, that's a connection one, it refers to this end, right? So what we can do is that we can add a related member that is continuous, right? And that is to be provided in the y direction. This is my y direction, so it has to be provided in this direction. So just provide it this way. So as you can see that here, yes, one RM, that's a related member, is generated at one end. Similarly, let us do one thing. Go to the next connection, which is essentially the other end of the analyzed member. So in a similar way, provide y also. So as you can see that yes, two related B members are being generated, that is RM2 and RM3, to which AM1 is connected, right? So now let us start editing the properties of RM2 and RM3 as per our requirement. So go to RM2. So what we do is that as far as RM2 is concerned, we can keep it as a, for example, as a HEA, right? We can keep it as HEA 300, right? So we can keep it as a, so edit. So let us keep it as HEA 300. HEA 300, okay, right? So okay, and then regarding the, see, as you can see that this analyzed member, I'm not interested in this analyzed member, in this RL, that's a related member. I just want to act it as a beam that will support my analyzed member AM1, right? So accordingly, I want to provide a small length of this member, for which I have provided y equal to -1 through the direction, and the length of each of this segment is at is 1 meter each, right? So you can see that this is a small piece, right? Okay, so now what we can do is that we can start providing what we call as support conditions. So in this case, what I will do is that I will just restrain the XYZ translations at both the ends, right? Now going to my RM3, and here again what I will do is that I will provide the same what we call as the same HEA 300, okay, and then the same member length minus y equal to -1 for the direction, and each of this length segments indicates 1 meter length, right? And in this case what I will do is that I will allow the translation in the x and y direction for this case, okay, and what I can do is, okay, and the end also I allow the x and y translations. Only the z direction, that's the vertical direction, is restrained. So now as you can see that, so this is how the support looks like. So let me just zoom it. Yes, you can see that here the three translations are being restrained. So that is how this is being indicated symbolically by the Idea Statica member. And on the other end, you can see that in this case only in one direction. Okay, the translation is restrained, that is in the z direction. So this is all about the member. Now here I would like to introduce one more thing, that is regarding the offsets, right? So if you see the, so now let me just zoom this. Okay, let me just go to the AM1 now. AM1, okay, AM1 we have HEA 240 only. So let me just go to HEA 240. So let me just edit it once again. Or what I will do is that I will just add another member that is good enough as a HEA 240. HEA, so this is our HEA 240. Okay, so that's okay. So here, if you zoom this, so as you can see that the analyzed member is of HEA 240, and all the related members, they are of HEA 300, right? This means that there is a difference of 60 mm, right, between the depths. So we want to ensure that yes, their TOS, that is the topo structures, are the same. So here you will find that both the analyzed member and the later members, they are having the different TOS. So let me just input the offset for the analyzed member. So here the difference in the depth is 60 mm. This means that I will offset an amount of say 30 mm here. So let me just say 30 mm, right? So here you will find that now the TOS are almost the same. They are exactly the same. You can say that, for example, if you see from this direction, that is the y direction, and just zoom it, yes, you can see that the TOS of the both the AM1 and the RMs are kept the same. So we have completely defined the members, including the AM as well as the RMs. Now it's a time for us to go ahead with the loading conditions. So here, first of all, the properties, we want to identify okay, whether it is a what we call as the ultimate limit state or is a serviceability. So in the first of all, let me define the ULS, that is the ultimate limit state. And so we will be applying the loading only on the analyzed member in this case. So here, as you can see that we are going to apply it at two locations. So, and in Idea Statica Member, we don't have any provision to apply directly a point load. Instead, a point load will be replaced by a distributor load that is spread over a very limited length. So in this case, what I'm planning is not to apply a concentrated load at 1.5 meters. I'm applying a distributor load that spans from, say, for example, say 1.45, from 1.45 to 1.55, 1.55, and the Z. So as you can see that the length of the loading, it is equal to zero point zero point 0.1 meters. So in order to obtain a concentrated load of say 90 kilonewton, I have to increase this to minus 900, right? So that minus 900 to 0.1 is equal to 90 kilonewton. So remember here, the very important aspect of the Idea Statica Member, it also allows you to specify the position of the loading. So here I am going to apply it straight on the top flange. So we have many options like top, bottom, left, right, etc. So and then the width. Width means this is the width of the loading, right? That is across the cross section. As you know, I am keeping it the same 100 mm. So we have properly generated the first load. Now let me also generate the other concentrated load. So what you can do is that you can just press here. Remember the loads, it includes the line loads on the analyzed member as well as the anti-forces on the related members. So on the analyzed member, I want to add one more loading. So I just apply this press button and ensure that we are in the same ULS also. So now I want to apply it to the other locations, that is 4.45. So I'll keep it as a 4.45, 4.45, then to 4.55, 4.55. So this means that I'm going to apply a load at a location of 4.5 meters. And similar to this, what I will do is that I will just apply it as a minus 900 and I will keep it at the same top flange. So you can just select the top flange. Okay, and you can also keep the same distance after mm. Okay, so as you can see that the concentrated load is also applied at the other location. Now in this case, I'm not going to apply any forces on the later members because they are the pinned supports. I'm not interested in that. So these are the loads that is associated with the ULS. Now I would like to add one more load condition, right? That is corresponding to the serviceability limit state. So what you can do is that you can just press this, okay, or you can copy the other LE1 also. So LE2 and LE2, I want to make it to corresponding to the so-called the serviceability limit state. So LSS characteristic I have added. Now I will add a load in such a way that in AM1 I can have it as a 1.45, 1.55, 1.45, 1.55, 1.55. So we can copy also the LE1 so that our job will be simpler. So in this case, as it is a demonstration, I want just again feed it again. Now here I want to apply it as a 35 kilonewton. So what I will do is that I will simply type minus 350 and I would like to apply it on the same top member, and let me keep the width as 100 mm, 100 mm. So then let me add one more line load, that is so you can say that. So let us keep it as a 1 point. So this is nothing but a 4.45. So 4.45, and this is my 4.55, 4.55, 4.55, and I want to keep it as a Here I think that we have not applied Z, so this should be 0 minus of 350 minus 350, and here also we should keep it as a minus 350 minus 350. This indicates that we have got two concentrated loads of 35 kilonewton each, right, at the two locations, and these loads are corresponding to the serviceability limit state for which we want to check the deflection of the member, right? And in this case too, we don't want to apply any kind of what we call as the anti-forces on the later members. So here I will just change it to the top, keep it as the top, and here we can change this also to 100 mm. Okay, 100 mm. Okay, so we have completed the loading also now. So we have generated two load cases, one corresponding to the ultimate limit state and the other corresponding to the serviceability limit state. Now let us go straight to the connections. So here, as you can see, that there are two connections. This is one location where connection 1 is required. This corresponds to connection 2. So now connections can be easily generated. So we have two connections between the AMs and the RMs, and they can be generated straight away through the Idea Statica connection. So what we need to do is that we just press a con. So as you can see that this is your con 1, connection 1, right? That is between the AM1 and this related member, that is nothing but the RM2. So if you want to describe or to specify connection, so you can straight away go to this button. So here it gives you all the details. That is, this is a connection between the members AM1 and RM2. So now you just edit connection. Now once you press edit connection, it will automatically take you to the Idea Statica connection GUI. That's a graphical user interface. So you can see that it's automatically started. So we need to specify all the connection details as usual in the Idea Statica connection. So yes. So now look here. So this is your RM1, this is your AM1, and this is your RM2. As you can see that their TOs are the same. So now let us start editing or making. Here I want to provide what we call as an end plate border connection between AM1 and RM2. And also, as you can see that here, just a minute, yes. So here I want to provide what we call as a cut also, a notch. So in order to provide a notch in the flange as well as the web of the AM1, what we can do is that we can straight away go for, so let me just provide it as a, so we can just add the manufacturing operation. And in the manufacturing operation, okay, so what we can do is that we can straight away add a cut. So here, so first I want to provide a cut in the flange. So you can see that both the flanges are overlapping. I want to provide a cut in the flange of the member AM1. So what we can do is that we can select it instead of the web, we can select a top flange, AM1 top flange, and we don't want a circle, we want only a notch. And the location we can keep it as a front. Okay, that's good enough. And based on the connecting members, we just select the this is my 155. So I'll keep it as a 155, 155, and let me keep it as a 240. So let me put the 240 here, 240 here. So as you can see that right now a notch is made in the flange, right? So that is just clears the flange of RM2. So now similarly we want to incorporate a notch in the web of AM1. So similarly what we can do is that we can just copy this. Okay, so we can just press this open one and we can just copy this. So and we can utilize this for generating a notch in the web of AM1. So here, so what we do is that instead of the top flange, we'll select the web one, and we want a notch, and we want it to be on the rear side. So you can see that here a notch is made in the. So we'll keep it as a. We want it on the rear side, and let us provide the dimensions of the notch. So we'll keep it as a. For example, this is 155, 155. The same notch we made in the flange, and the cut I will restrict to 30 mm. So you can say that yes. So let's just see how does it look like. Yes, as you can see that yes, we have generated a notch in the web also as shown here. Now I would like to introduce an interplate border connection in order to transfer, okay, the forces from AM1 to RM2. So as usual, what we can do is that we can go to the operation, and here we have got the plate connection, and let us select the so-called bolt. So we select the 8.4 bolts of what we call as a M22. So let us keep it as M2, or let us keep it as an M24. So okay. Yes, so as you can see that yes, an end plate is automatically generated, which we need to edit. So this end plate. So let us start editing the dimensions. Okay, so we can look into the sketch. That's the best way to adjust a connection as per our requirement. I'll just highlight this end plate and just go on editing. So here the material plate we have kept as 235, and let us keep it as an 18 mm, right? And what we can do, so instead of 18, for example, let us keep it a little bit less, 16, and there's a bolter connection, and this is to the profile. So this, as you know, it's used, these dimensions are used to uh, rearrange or to modify the sizes of the end plate. So here accordingly what I will do is that I will keep it as a minus 30. So I'm very confident that you know what these parameters are, so I don't want to just spend my time on this. So I'm just repeating minus 30, minus 15, and again the same minus 30, minus 15. I just sorry, so minus 30, minus 15. So this is my minus 15. So as you can see that yes, so our end plate is ready. Now we want to make some minor modifications to our boards. So as far as the boards are concerned, we have so we can just keep it. We have M24 8.8 that we have already selected, and let us keep it as say the top. We'll keep it as a minus 80, minus 80. That's our first bolt line, minus 80, and the other one we'll keep it as a minus 70. Okay, minus 70 instead of 0. I want to provide it directly through this. Okay, and the left what we do is that we can keep it as a minus 60. So we'll keep it as a minus 60 here, minus 60 here, and the bottom it is not relevant because the bolt row I have already represented through the top layers, and the right, for the right what we can do is that we can keep it as a minus 60. So we can keep it as a minus 60 here, minus 60 here. Yes, so you can see that all the boards are being we have got only 4 boards that is being properly positioned here. So it's an HA 240 member, and regarding the, so we'll keep the shear force interface the same, and the flanges as we know that there's no connection with the flanges, so it is not relevant to us. And coming to the welds, you can corresponding to the web, we can say that is made to be a double-sided fillet weld of 3 mm size. Okay. Anyway, please remember that the connection adequacy or the verification will not be carried out in Idea Statica member. Rather, if you want to verify a connection, you have to go directly. You have to model the connection and then verify it in Idea Statica connection only. Okay. So as you can see that yes, connection 1 is ready. It is acceptable to us. Let us save this. You need not to just remove this. You can just keep it down. Okay. And so the connection 1 is, once the connection 1 is ready, ensure that you just save it, because you want to copy this connection at the other end also, because we know that the connection, so as you can see that the connection is automatically transferred to the Idea Statica member. So this is how it looks like. Okay, it is automatically transferred. Now as you know that we have got one more location where the connection need to be modeled, right? That is this location. So what we do is that we go to connection 2, and in connection 2 I want to use the same connection of connection 1. So as you can see that here I have already have the connection 1, so you can just select it and then apply. So this ensures that the same connection is applied here. Yes, with a minimum effort you could make this connection readily available to you, right? So look here, so we have, yes, you can see that our connection is automatically developed for the other end too also. So, and for this tutorial, we don't want to add any kind of operations here. And one very important thing I just want to tell you is here the beam that we are considering is a laterally restrained beam, right? It's a laterally restrained beam. So laterally restrained beam means that we have some mechanism, right, to control or to restrain the movement of or the out of plane translation of the compression flange. And this mechanism we used to provide when I was working in the industry. I used to provide either a plan bracing that can effectively control what we call as the outer plane, the translation of the compression flange, or it can also be okay, restrained by means of some constructions. For suppose that you are having a beam that supports an corrugated RCC deck slab which is being connected to the compression flange through the studs. In that case also you can assume that the beam is fully restrained, right? So in this case, remember the buckling effects are not relevant to us. So here we will not do any kind of LBA, or we will not do any what we call as the buckling analysis with the imperfections, that's the GMNIA. We will perform only one analysis, that is the material nonlinear analysis, because for this case where it's a restrained beam, it is not relevant to us. Okay, so what we need to do is that we have to straight away go for the calculate button. So let us see. So as you can see that the analysis will take say 5 to 10 seconds time. So what is very important is I want to just provide a small piece of advice to my engineers. That is, you must be able to verify all the calculations provided by Idea Statica through your simple hand calculations. That's very important, because getting that solution through a computer do not provide any guarantee that it is correct. You might have committed minor mistakes in the input of the geometry or the input of the loads. You must be able to ensure, or you must be able to tell to your client with confidence, yes, the analysis results are acceptable to me. So yes, as you can see that the MNA, it is 100%. It is good for means that the beam is able to resist 100% of the loads, and as you can see that the strains are less than 5%. And here, please remember, Idea Statica calculate the plastic moment of resistance of a section, which is the strength capacity or the strength of the section directly based on the strain levels. Now, in Idea Statica, a limit of 5% is considered as a target for the calculation of the plastic moment of resistance, right? So, in this case, you can see that you have not reached the plastic moment of resistance because the strains are very much less. It is near to zero only. But and at the same time also you see that the beam is able to take care of the 100% of the loads. So now as usual, let us start evaluating and start reviewing the various results provided by the Idea Statica member. So you can straight away press a check. So let us just go for okay, in this case, so let me just rotate it a little bit. Okay, this was good enough. Okay, now look here. So this is so as I already told you. So we have got the analyzed member being completely modeled using the shell elements, and only a part of this RMs, that's the later members, are modeled using the shell elements. The balance that is shown as a straight is being modeled using the 1D beam elements. So now let us go for the review of the results. So the strain checks indicates that we have got only a 0% strain. That means the material is not being taken to the yield levels, right? That means beyond the yield level, I should say. And now so that's all about the strain levels. And now let us go for the stress. Yes. So you can say that, okay, please, while reviewing the results, please ensure this button. And here I want to see stress and strain only here. That is in LE1. That is my extreme case. So take some time to refresh. So yes, so this is your stress level. So as you can see that a major part of this flanges, whether it's a top flange or the bottom flange, that is taken to the yield stress level. But obviously, as per our understanding, we know that the plastic moment of resistance, okay, corresponds to a case when all the fibers are subject to the yielding. So here you can see that still some portion of the web, it is still under elastic condition, it is not yielded. So it does mean that the beam has got some kind of a reserve strength. So this is all about the stresses, right? So right. So now let me just take you to the deformed shape. That is, so this is what you can do is that you can just press the UZ, that is a vertical deflection. So the window is up, refreshing. So this is the vertical deflection, and remember you have to be very careful regarding this window, which load case is to be selected. As we know that the deflections are to be read only from for the serviceability in this case. So I have to select LE2, right? So let us see what will be the deflection. So the UZ, so we can see that is a 14.6 mm. Obviously, this 14.6 mm has to be compared with the limits provided in the codes. It could be L by 250, L by 300, etc. Depending upon the type of the flooring that it supports, right? So accordingly, you can verify whether the beam is good enough for serviceability or not. And finally, I just want to, so let's just keep this. So as you can see that there's a button on the deformed. So if you just press it once again, it comes to the undeformed condition. Yes, it's undeformed condition. So now this idea static also provides you how to visualize the so-called internal forces. So you can just press this internal forces here. And the internal forces. So what you can do is that you can select the my. So look here, this is how the Bendimont diagram looks like. Actually, there is some kind of a what I feel is that a scaling problem. So let me just remove this meshing also, so that is a little bit more clear to you. It is important that you verify this. Look here, you know that we are applied to two concentrated loads, right? So let me select instead of LE2, we are interested in LE1 because the bending moment is relevant to the ultimate limit state is important to us. So here, as you can see that, okay, so this beam is subjected to a concentrated load at two locations, right? So accordingly, you can see that it is a trapezoidal bending moment diagram. This is a trapezoidal bending moment diagram, and we find that the peak value of this bending moment is 135, right? And look here, and here also you'll find that due to the support rigidity, some kind of a minimum. This is not truly pinned, so there is some kind of a small amount of a bending moment getting developed over here. Anyway, that is not going to have any kind of an effect on our final results. Now, similar to the bending moment, you can also visualize the so-called shear force diagram. You can just press the VZ button, and the VZ button will provide you what will be the shear force variation. So you can just see it here. So you can say that yes. So let me just keep it as plain spot. Do not have any kind of other colorful. Yes. So you can very well see that yes, this is how it is subjected to a concentrated load. So obviously we know that it should be something like a triangle. Here you will find that the shear force, when it's a point load, it has to be vertical, but this was a small distributed load that is applied at this location where the strains are a little bit higher, as you can see. So it suddenly decreases down through a linear fashion. It's not an abrupt drop. And in this portion between the concentrated loads, we are having practically zero shear force, and you can see that the shear force increases right towards the supports. So this is all regarding the shear force distributions, and so we have seen that the member has sufficient capacity, and the strains are below the 5% level, and we also find that the serviceability limits and deflections are also verified. So, and Idea Statica also provides you one more facility, that is to find out the reactions. As you know that we have three supports, four supports, one, two, three, four supports. So we can find out what will be the total reaction, right? So what you can do is that you can just press this reaction. So you can find out, yes. So look here. So this is how the reactions are. So you can see that, for example, in LE1, we have 45 kilonewton, 45, 45, 45, right? And as you know that here we applied a total of right 90 plus 90, that's 180 kilonewton. So that is equal to 45 into 4. So it's already in equilibrium. We don't have any problem. It's important that we check all these things, right? So it does mean, and as you can see that MNA on the right side when you are in the, so you can see that the screen there's a input on the right, the output on the right side. It provides you the stresses as well as a 235.1. As you can see that it is the maximum stress in the top flange of the M1. You can also see the stresses in the various components like the top flange, the bottom flange, and also the web. You can see that on the web the maximum stress is slightly less compared to the flange. And RM2, RM3 we are not interested right now. And then connection 1 and connection 2, don't have the impression that it has verified all the components. It has just provided you the stresses in, for example, the end plate only, right? You can see that the contact stresses in the end plate the bending stresses. These are the bending stresses in the end plate. They are of the 94 MPa. So that is not a problem to us. So it is important that we verify all these connections straight away in the Idea Statica connection. Now finally you can go for the report session, and the report session it provides you all the summary of the analysis results. But unfortunately, as I already told you, it do not provide any kind of the numbers relevant to what is the full plastic moment capacity, and the case of the LTP etc. It do not provide you uh, especially the guidance regarding what are the critical buckling moments etc. And also it does not provide exactly how much is the factor of safety available to us. So a lot more modification or the improvements have to be made to this Idea Statica report for the Idea Statica member. Now here, for example, if you want a detailed report, you can just press these buttons. So you can just refresh it once again. But in spite of that, whether you go for the detailed report, you don't have much of the information as you will see right now. So it is important you just start solving the problems, okay, and manually verifying the same. Not aware. So you can see that here are the details regarding the analyzed members, and then these are the details regarding the later members RM2 and RM3, and all the sketches of the cross sections are given for the AM as well as the AM as well as RM. So here then you can see that regarding the loading details that is already input into the program, and then it directly provides you the results. So it just provides you, yes, the beam is good enough for the 100% of the loads, but did not provide you any kind of a guidance how much capacity is left over, right? So this is the so-called equivalent stress for the LE1, that is for the ultimate limit state ULS condition, is the LC1, equivalent stress LC1. So you can see that here it has gone up to the maximum stress of 235. That is only the flanges. It does mean that still we have got the web left over. So obviously it is understood that the section do have some capacity. So what you can do is that, to obtain the correct value of the moment of resistance, so that you can check it with the calculated value, you can just go on increasing the loads till a stage is reached where the strain is 5%, and you can just cross check. In this case, I have cross checked, and I've observed that, okay, the calculated moment of resistance, the plastic moment of resistance by Idea Statica almost matches exactly with the plastic moment of resistance obtained by the Eurocode. Okay, and then it provides you the plastic strain distribution, where we find that the strains in this case are only at a zero level, right? And also it provides you the stresses in the various parts of the analyzed member as well as the later members. So it covers basically the bottom flange, top flange, and the web of the members. And regarding the connection, it provides you the stress levels in the end plates, and then it also provides you the design data. So you can see that the material is S235, right, and all the simple explanations are given. So this is all about the simple tutorial on the how you will go for the design of a lateral restraint beam. So in the next tutorial, I will take up a similar example, but it will be done not as per the Eurocode, but it will be done as per ISO 800, because many of my friends are going on coming with the same request. Why don't you upload any tutorials covering the Indian standards, right? So I felt it is a time to start uploading some tutorials on IS 800 also. So that's all about. So please start making your own tutorials examples first. Before entering into the Idea Statica, make a detailed hand calculations from your side, and then compare the results of the Idea Statica. This is how you learn a software in a better way. This is just I am telling based on my experience. So okay, till then, bye. So we will see next time with a new tutorial.